Good afternoon, everyone. It's really wonderful to be back in Tokyo. And today I will be speaking about our work at Entropica and what we are building. We are creating the very large-scale design software for fault-tolerant quantum computing. And our objective is to empower developers, researchers, and the domain experts to manage the quantum error correction layer of the stack effectively to fully unlock the power of quantum computing. If you're not familiar with our work yet, we are a quantum software company born and raised in Singapore. And we actually have many years of experience working with multiple players in the industry, including hardware companies, government agencies, and large corporations. And something that I think is very interesting that we have always learned throughout all the work engagements that we had is that there is always one lesson. And the lesson is that the kind of problems that we care about, the kind of problems that I believe everyone in the audience cares about when it comes to solving them with quantum computing are actually incredibly hard. They are so difficult that most likely they are going to require very large-scale quantum computers with fault tolerance. But fault tolerance needs quantum error correction, which is a topic that we have heard a lot today already, and we're going to hear more, I believe, in the coming sessions. And the need for quantum error correction actually is very intriguing because it makes the quantum software stack very different from the classical conventional software stack. It introduces new challenges, and it also introduces new design choices that we need to make. In fact, what I would say is that the challenge really is twofold here. On one end, everyone is familiar with the problem that we need more higher quality qubits. We need hardware with more higher quality qubits. What I think is a bit more subtle is that on the software side, we actually need new software tools to define and manage logical qubits. And this is why at Entropica we are building the software infrastructure to enable large-scale fault-tolerant quantum computations. Now, I like analogies a lot, so I'm gonna give you an analogy to really illustrate the kind of problem that we are facing. Imagine we want to build a beautiful tapestry. We want to weave a tapestry. And we have all the components that we need. So we have the finest silks, we have the wool, we have all the dyes. But the challenge here is that to weave the tapestry, we can only use a single needle. And you can appreciate how difficult that is going to be. And it's very similar to the situation we are facing in quantum computing today. We know what we need to do. We have a good understanding at the theoretical level of quantum error correction, and we are starting to have better and better quality qubits. But we are missing something like a loom. We are missing the tools that allow us to weave everything together into a fault-tolerant fabric. And I would go as far as saying that, in a way, we are really facing, or at least we need to overcome this fault-tolerant quantum error correction barrier, which is something intrinsic into the nature of quantum mechanics and intrinsic into the nature of quantum computing. And there are multiple challenges here. I've already said that we need to be able to correct errors on quantum computers. But that is very easy to say, but it turns out that quantum error correction is actually an extremely difficult topic. And most of you here are either working on hardware, algorithms, software solutions, and I believe you know, that when you try to embed error correction in your work, you will very quickly face a very steep learning curve. It's just really hard to deal with quantum error correction overall. And when you want to introduce the concept of fault tolerance, which means being able to correct errors faster than they actually happen or accumulate on a quantum computer, well, the beauty of fault tolerance is that it's pretty much still an art today. And we are still relying on designs introduced by very few experts worldwide. I would go as far as saying that as an industry, we really lack the software tools to design, test, and implement fault-tolerant quantum error-corrected programs. So at Entropica, we are very familiar with these problems. And this is why we are building the Quantum Loom, which is a software platform to design fault-tolerant quantum computations. And in this talk, I'm going to introduce to you how this works and what we already have. So this is the intuition, right? Think of it as a quantum program weaver, and this is why the analogy with the tapestry. So the input is a high-level quantum program. It's the application that you want to solve with a quantum computer. And together with that, you're going to weave a quantum error correction code and the features of the hardware of the quantum computer that you wish to use. And the output of the quantum loom is a fault-tolerant executable program, an implementation of that program in a fault-tolerant way that can run on a quantum computer of your choice. Because our goal at Entropica is really to empower all of you to fully focus on the problem that you want to solve without having to worry about how to implement fault-tolerant error correction. This is what we wish to do. And in that way, we are building a central part of the quantum software. And if any of you is focusing on one of the complementary aspects, like the hardware, or maybe the decoding, the algorithms, or the quantum control, and you want to introduce error correction in your work, we are your partners for the journey. Now that I've given you an introduction to what we do, I really would like you to appreciate how we work and how we think in the company. So we love to think and work as developers. And in fact, we have adopted 3 software engineering principles that are key to everything we do, but are also key to addressing the challenges that we are facing in fault-tolerant quantum computing. The first one is scalability. Most likely, we are going to need millions of physical qubits to implement fault-tolerant quantum error correction. And we'll need to be able to track the relationship between the qubits. But what I think is very interesting is that every time you have a new challenge, you also have a new opportunity. And the opportunity here is, how do we think about new data structures for quantum error correction? And I will say a few more words in a second about that. The second principle is user-friendliness. We believe that using a quantum computer should be easy. It shouldn't be difficult. I'm a physicist. I know that most of the people who started the field at the beginning were physicists, and we love to make things complex. At Entropica, we want to make sure that what we build is tailored for developers. We believe in graphical user interfaces. We believe in allowing users to work at the level of confidence that they have, either automating everything or going down to the details of the error correction codes that you're working with. Last but not least, research readiness. I'm very well aware that the goal of fault-tolerant quantum computing is the long-term goal of the industry. But everything we build today is already useful. We make sure that we can accelerate, that we can improve your research from day one. Okay, things are going to get a bit more technical. And I really want to show you how the stack that we are building looks like. I mentioned the problem of data structures, which is actually a really beautiful problem. And at the center of the Entropica stack, we have a data structure to manage quantum error correction codes, which we call the ECA, which is actually a Sanskrit word that means unique, one, single. And we call it that way because the ECA contains all the information of the problem that you want to solve with our stack. Okay, in fact, before I continue, I would like to ask everyone in the audience one question. Can you please raise your hand if you have views or if you're using IBM Qiskit? Okay, there's a lot of hands. Fantastic. Thank you. I started to use Qiskit in 2016, pretty much when it came out. And I would say that one of the great innovations that IBM introduced at the time were data structures to manage quantum computations. Because we need data structures in quantum computing just like we do need them for classical computing. But the interesting problem here is that we didn't have data structures for quantum error correction codes. And this is why at Entropica we have introduced the ECA, which is a programmable, scalable, descriptive way to manage error correction codes. And we have exposed multiple APIs, so you can construct ECA instances easily, both graphically and programmatically. And we are already able to interact with other software tools like Steam, Crumble, and Qiskit, so you can easily transfer information across. And the ECA really sits at the middle of our stack, and it is embedded within a suite of utility and development tools. And we divide them into 3 classes, if you like: convenience functions, utility functions, and application functions. I've already mentioned convenience functions. Basically, these are all the ways that you have to program the ECA effectively. I will focus a little bit on the second one. Again, when you think like a developer, you will know, in fact, most of you, I believe, are developers here, you will know that you spend a lot of your time debugging your code. Because when you write code, it's very easy to have errors, and you need to make sure that everything works as it should. And a lot of our efforts in Entropica are there to make sure that we have ways to validate the formal and functional correctness of the information in the ECA. This is really, really important. We believe this is going to be a key topic moving forward, how to debug effectively quantum computations. When it comes to applications, we have everything we need to transform our information into an executable that can run on a quantum computer. But it also includes simulators, so ways for you to test, ways for you to visualize the data that you have, and ways for you to store, archive, and retrieve your data. So this is the structure of the Entropica stack. And in the second part of my talk, what I will do is to show some of these tools in action, so you can better appreciate what we have. Everything you see on the slide is already available today. And we are able to implement a full workflow so we can investigate the properties of topological quantum error correction codes. But obviously, there is too much here for a 20-minute talk. So what I will do is just to focus on the clear blue boxes, show you how to design quantum error correction codes effectively, show you how you can validate the code, and how to archive and retrieve data. All right, let's see if this works. Yes, perfect. So it is a bit different from the other formats. There will be a little demo moving while I speak. So what you're seeing here is the tile assembly tool. So this is a graphical user interface we have developed in Entropica, which allows you to design the pattern of topological error correction codes. So if you're familiar with the surface code, if you're working with the surface code, you will know what's happening here. The user is positioning the different tiles that define the stabilizers, that define the structure of the error correction code. And the beauty of it, the simplicity of it, is that it allows you to do it really, really quickly. Because the alternative is you code everything by hand, which is incredibly ugly, is the way we used to work, and is just not efficient, especially if you want to work with hundreds, thousands, or millions of qubits. So you can easily edit the pattern, and as the video proceeds, you will see also how you can work with custom tiles, or with twist defects, and so forth. Another feature that you have is that you can work with different layers. For example, with the surface code, you need to be able to implement lattice surgery operations. And by working with different layers, you're able to compare and work with changes in the code, which is key for lattice surgery. Furthermore, what you can do, you can create graphically the structure of the code, and then you can export everything into the ECA. So now you have the data, and you're ready to work with the data in your workflow. And one of the things that you can do is to create the little parts of the circuit that you need to implement the error correction code. And the video is a bit longer than my speaking time, so I'll move to the next slide. And the next slide is about how to verify that the snippets of code that implement your error correction surface code work as they should. It goes back to this idea of validation, of debugging. As I said, just like for classical code, we expect to have access to ways to test the validity of what we are doing, or what we are programming for quantum computers. And the example that I'm going to show you here is a very technical example, but it's a neat one. In error correction, usually what you do, you need to extract information about the kind of errors that are happening on your quantum computations. And we call that syndrome extraction. For that to happen, you need to write a circuit that implements the syndrome extraction on your quantum computer. The problem is that we don't really have a book that tells us how to do that. So you need to write the code yourself. Well, I'll show you something here. This is another graphical tool we developed. And what you're going to see two implementations of the same syndrome extraction circuit for a surface code. In fact, let me start the video. One of them is correct. The other one is missing one gate. And if I just let it run, maybe some of you will spot it, but I think it's very difficult to see where the error is. And in fact, now we are using a graphical user interface. If you were to check your code, it would be even harder. The point here is that you can pass the circuit information to our validator, to our software tool, and literally with a few lines of code, is going to give you key information. It's going to tell you, be careful, because on one of the circuits, there is a missing CNOT gate between qubit 12 and 21. And in fact, if you were to go back, you might have spotted that at the second time step, there was a missing CNOT gate on the left computation. But if you do it by hand, it's just tedious and incredibly hard. We want to automate all these processes so that you can program your quantum computers more effectively. The last example I'm going to show you is how to store and save in data. When you work with quantum computers, what happens is that the result is going to be given to you as a sequence, as a list of zeros and ones. The problem is of that, and I know it because I've committed the mistake so many times, is that you're going to save the data, and then you go back 2 weeks later, you look at the data, you have no idea what you're looking at, because you have lost all the context of your computation. So at Entropica, we've built the EDB, which is the experiment database. It has a visual interface. Oops, sorry about that. Let me go back. It has a visual interface that allows you to check all the computations that are running, that have been saved. Let's see if I can start the video again. Yes, great. And it allows you to store any serializable data that you can produce during the workflow. And furthermore, what you can do, you can add a lot of context to it. You can attach metadata to your computing results, which means that you can go back at any time and you know exactly what you're looking at because you have saved the context together with the results of the computation, which makes it so much easier to collaborate across teams within a larger team, or especially if you want to run machine learning or if you want to do data mining or your computation data, now you can, because everything is labeled from the very beginning. And this solution has been a game changer for us internally. Overall, our software tools make it so much easier and so much faster to work with quantum error correction codes. And I think it's incredibly exciting because we are opening up new possibilities towards fault-tolerant quantum computing in design, debugging, and visualization. And what is really important is that our software tools are already available for testing. And I can announce today that we are going to be releasing the Entropica Workbench, which is a comprehensive graphical user interface to design quantum error correction codes at the beginning of 2025. So, if you're interested in our work, if you're working on quantum error correction, if you want to start embedding error correction in your work, our mission, our goal is to facilitate your transition towards fault tolerance. So please come and talk to me at any time during the 2 days of the conference. My colleague Jing Gao, our head of product, who's raising his hand, is here with me as well. And I would just like to thank you for your attention, for your presence, and I wish everyone a wonderful time at Q2B. Thank you so much.
Thank you. We have one question from the audience, so I'll just read it out very quickly. Has the GUI been tested on any existing hardwares? Does the GUI impose any limitation on the geometry of the hardware?
This is a very good question. So for now, the GUI is working with the topology that you've seen on the slide. But in principle, it does not put limitation on the kind of hardware that you want to use. And yes, we've been testing the workflows that I have shown already on the IBM systems. So thank you for the question. And we really want to make sure that you will be able to work with ideally any quantum error correction code. I've shown the surface code as an example, simply because it's very well known. It is a great way to get started, but it will not be limited to that family of codes.
Excellent. Thank you again, Tommaso.
Thank you. Thank you, everyone.